At the core of calculus is the limit. But what actually is a limit? In order to understand limits, we will first have to understand discontinuities. Now, there are three different types of discontinuities. There are removable discontinuities, where it is just a hole in the function. There are jump discontinuities, where the function seems to jump from one value to another. And there are infinite discontinuities, where you will see vertical asymptotes. Now, discontinuities are just areas where the function is undefined at a certain value of x. But limits allow us to sort of define these values by analyzing the function's behavior as it approaches that value of x. I'll show you what I mean. Consider the function x minus 2 over x squared minus 5x plus 6. As you can see, this function has multiple different types of discontinuities. There's both a removable discontinuity and an infinite discontinuity. We can't do anything about the infinite discontinuity, as the function is approaching both infinity and negative infinity. But we can see something neat around the removable discontinuity. As you can see, it seems to approach some value as x gets closer to 2. So what we can do is we can use a limit to evaluate somewhat what this value is as x approaches 2. The function we are considering is x minus 2 over x squared minus 5x plus 6. Now, since we are trying to find the value at x equals 2, which is normally undefined, we write this symbol, limit, as x approaches 2 of the function. Now, as you'll see, the denominator is a quadratic that can be split into two factors, x minus 2 times x minus 3. So our new expression is the limit as x approaches 2 of x minus 2 over x minus 2 times x minus 3. The x minus 2 in the numerator and the denominator can cancel out, leaving our expression as just 1 over x minus 3. But now, since plugging in 2 won't give our function a value of undefined, we can go ahead and use direct substitution and plug in 2 for x. So we get 1 over 2 minus 3, which is equal to 1 over negative 1, which is just equal to negative 1. Now, the reason why the value x equals 2 is a removable discontinuity rather than an infinite discontinuity like x equals 3 is because x minus 2 is a factor in both the top and bottom of the function, meaning that they can cancel. So overall, the x minus 2 doesn't really have an effect on the function, but when you plug 2 into the original function, you get an expression that is in the indeterminate form of 0 over 0. Whereas if I plug in 3, I will get some number, in this case 1, over 0, which genuinely approaches infinity or negative infinity. You can see how limits can be used to sort of evaluate a function at a value where it would normally be undefined. Next, I want to talk about jumping discontinuities. Let's consider this piecewise function. Notice how it seems to jump from one value to another. Now, this is an example of a function that we can't take a limit of as a whole. We'd have to take a limit from the left and a limit from the right, because a general limit does not exist. And in order to fully explain this, I want to introduce something called the epsilon delta definition of limits. This is the epsilon delta definition for limits. And although it might look a little bit intimidating at first with all the different symbols, it's actually a pretty simple statement. And this isn't really necessary for high school calculus, but I do think it is a good thing to think about and appreciate in terms of how limits actually work. This simply reads, the limit as x approaches a of f of x equals L, therefore saying that the limit exists, if for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. This is pretty much saying that as x gets within a tiny region between a, so like a plus 0.1 and a minus 0.1, that means that f of x minus L is less than epsilon. So in other words, f of x minus L is getting very, very close to 0 because epsilon is very, very close to 0. So this is pretty much saying that for all areas around A, f of x will get extremely, extremely close to L. And I'll show you what this looks like visually. Let's consider our old function, x minus 2 over x squared minus 5x plus 6. In this case, delta will be the distance between the orange lines, or the distance between the x values, and epsilon will be the distance between the purple lines, or the distance between the y values. What we're looking for here is that as delta goes to 0, or as x goes to the value a, the function or the y values will approach a certain value on both sides. So let's see what happens. As you can see, as the x values get closer and closer to 2, which is where the removable discontinuity is, these y values seem to be approaching the exact same value of -1. This means that this function follows the epsilon delta rule for limits, and thus the limit exists as -1, because no matter where you approach 2 from on the function, the behavior of the function will always approach the same value of -1. Now let's go back to our piecewise function. And again, delta is going to be the distance between the orange lines, or the x values, and epsilon is going to be the distance between the purple lines, or the y values. Now let's see what happens when we get closer and closer to where our discontinuity is. As you can see, there is still a wide range between the epsilon values, even as the delta values go to 0. This means that this limit doesn't exist generally, and you would have to take a limit as x approaches the discontinuity from the left, and also take a limit as x approaches the discontinuity from the right. This goes against the epsilon delta definition for limits because it doesn't work for all epsilon greater than 0. It only works for epsilon that are greater than the range between these two lines. You may have noticed that I said taking a limit from the left of a function and taking the limit from the right of a function. But what does this really mean, and how do we denote it? Taking a limit from the left of a function means ignoring the right side, how it behaves on the right side of the number, just thinking about it as it approaches that number from the left. So really analyzing only the function's behavior on one side of the number. We denote this with a negative sign in the exponent. So in our case, it would be limit as x approaches 2 from the left of f of x equals 1. It is similar for taking the limit of a function from the right. But instead of a negative sign in the exponent, it is a plus sign in the exponent. And this would be limit as x approaches 2 from the right of f of x equals 2.5. Essentially, for a limit to exist, generally, both of these limits have to be the same number. But since these limits are not the same number, the limit does not exist, as limit as x approaches 2 of f of x cannot be determined. So far, we've been thinking about limits either graphically or in ways that we can get the limit out of indeterminate form. But how would you evaluate a limit if you can't assess the function's behavior visually with a graph, or mathematically extract the limit by canceling something in the numerator and the denominator to take it out of indeterminate form? In order to do this, we will have to plug in values that are close to our a value, and then put them in a table so that we can see what the function appears to be approaching on both sides. Let's consider the function sine of x over x, and say that we are trying to find the limit as x approaches 0 of the function. There's nothing that can cancel in the numerator or the denominator, and we can't see the graph. And if you just directly plug in 0, you get 0 over 0, which is in indeterminate form. Here I have limit as x approaches 0 of sine of x over x, and a table that I will fill in with values as x goes to 0 from both the positive side and the negative side, so that we can see numerically what the function seems to be approaching as x goes to 0. You can plug in these values yourself and make sure it works for you, but I'm not going to go through the process of plugging in these numbers repeatedly. As you can see, this function clearly seems to be approaching a value. It is very obvious that it is approaching 1 from both the positive side and the negative side, which means both that this limit exists and that it is approaching 1, as sine of x over x goes to 0. So now, even though we don't have the graph and we can't mathematically extract the limit without other methods, we can see that this function seems to approach 1 as x approaches 0. Overall, I hope this video helped you gain an understanding of the basics of limits and kind of how they work. In future videos, we will go over more advanced methods of evaluating limits and more mathematical methods, but I will leave some practice problems for you to do on the screen, and as always, if you have any questions, leave a comment and I will try my best to respond. I hope you have a good day.